Hello and welcome back. The next topic for discussion is cycloalkanes. So we're going to talk about cycloalkanes, and specifically we're going to look at some different conformations or different ways that cyclohexane can exist. So which conformations can it adopt? And we're going to look at different ways to draw cyclohexane and its derivatives. Okay? So getting started, we understand what a cycloalkane is. We've looked at them a little bit. But what were their conformations? What do they actually look like in a 3D space? Well, they're not exactly flat. We might think of them as being flat because that's the way we usually draw them. But if they were flat, each carbon in the ring would experience some significant angle strain in most of these rings. So for a 3-carbon ring, we have a 60-degree angle here. And in fact, really for a cyclopropane, it pretty much is pretty close to 60 degrees. For a 4-carbon ring, we'd have a 90-degree angle if they were flat. A 5-carbon ring would be 108. A 6-carbon ring would be 120. A 7-carbon ring would be 129. And an 8-carbon ring would be 135. Remember, if we have a tetrahedral carbon, what is our bond angle between those carbon-hydrogen bonds, say for methane? They're 109.5. So that's our ideal sp3 hybridized carbon bond angle is 109.5. So the closest one here for a flat system would be this cyclopentane at 108. So also if a ring was flat, then all of the carbon-carbon bonds would be eclipsing each other, and that would have torsional strain. So like in other words, we'd have some hydrogens here on top of each other and they'd be pushing each other apart. But we don't really see that, and how do we know they really don't adopt these type of conformations? Because if we look at the heats of combustion per CH2 group, as we move across, as we increase in the number of carbons, we can see that the heat of combustion is highest for cyclopropane. Okay, remember that 60-degree bond angle? And then we have cyclobutane with that 90-degree bond angle. And then the rest of them, as we go from 5 to 12, are pretty close to each other. Not a huge difference. So what we're seeing is that we don't see this significant increase. So we would expect cyclopentane to have the lowest heat of combustion per CH2 group. But in fact, we don't see a huge increase as we go from 6 to 7 to 8 carbons. So why is that? It's because they adopt a different shape. They're not completely flat. Now, cyclopropane is pretty close to that 60 degrees. There's nothing you can do about that. It's 3 carbons, right? And that's why the heat of combustion is so high per CH2 group. But cyclobutane is going to pucker a little bit, and it can adopt a bond angle of about 88 degrees. Okay, so it's still a little bit bad. And it has some torsional strain. Okay, this is for cyclobutane. But we're showing cyclopropane here on the right, so that's kind of strange. We have some torsional strain because these carbon-hydrogen bonds are going to kind of eclipse each other. Okay, so we also have some strain for cyclopropane. You can see here it wants to be like along these red lines, but it's just not going to be able to adopt that because we have that 3-membered ring. When we get up to 5 carbons, we don't have as much angle strain. Remember, it was pretty close to that 109.5, and it even puckers a little bit to get it a little bit closer. Okay, so cyclopentane is only 5 kilojoules per mole, less stable than cyclohexane, and we're going to see that cyclohexane is pretty close to that 109.5. So cyclopentane adopts what's called an envelope conformation, so it puckers a little bit to be able to get it pretty close to that ideal angle. So here we have cyclohexane, and it can adopt a lot of different conformations, but it's not flat. Its common conformation here is a chair conformation, where one of the carbons will be down, the next one up, the next one down, the next one up, the next one down, the next one up. Okay, so if you have a model kit, build a model of cyclohexane so you can see this conformation. You're going to see this chair conformation if you build a model with your model kit. So cyclohexane can go from the chair to a half chair to a twist boat to a boat where both of these N carbons are up, to a different twist boat, to a half chair, and then back to another chair. So basically, cyclohexane can flip, this is called a ring flip, from the first chair conformation to the second chair conformation. On the first chair conformation, if we call this carbon 1 is pointing up, and on the second chair, this carbon 1 is pointing down, okay? So this would be 1, 2, 3, 4. C4 here is pointing down on the first chair, and C4 is pointing up on the second chair. So we're not flipping the molecule over, even though it looks like that's what's happened. We're moving the carbons until we get this conformation where C1 is gone from up to down, C4 is gone from down to up, and everything else is up, down, up, down. So remember, ideally, when we draw an alkane, we draw it in this line angle formula. And if you look at this chair conformation, you can see that it's basically a line angle formula where the angles are approximately 109.5, where it's just in a ring. So it's down, up, down, up, down, up. So cyclohexane has no ring strain because it is in a chair conformation. It isn't forced into those unusual angles. It doesn't have angle strain because the angles are 109.5, just like any other sp3 hybridized carbon. And it doesn't have torsional strain, so these hydrogens don't repel each other, because in the chair conformation, all of the CH bonds are staggered. So the hydrogen up here is at what's called an axial position, and the next hydrogen is in an equatorial position. The next hydrogen is axial, and the next up hydrogen is equatorial, and so on. So they don't repel each other. So if we look at a Newman projection for cyclohexane, you can see that we're looking at, well, in fact, this is kind of flipped over, but what we're looking at is, say, these back two carbons from the opposite direction, okay, and then this one in the middle is going down. You can see that it doesn't have any strain because these hydrogens are all staggered from each other. They're not eclipsed in that chair conformation. So to draw a chair conformation for cyclohexane, we draw, let's just go to the next slide. We draw two parallel lines. Okay, let me go ahead and get a different color here. We draw two parallel lines pointing up, okay, and then two parallel lines like this, and then two parallel lines pointing with a negative slope, okay? All right. So each carbon in the ring has two substituents. One of them is going to be axial, okay, either pointing straight up or straight down, like this X, and the other is going to be equatorial, either pointing out and up or out and down. Okay, so axial positions are above and below the ring. Equatorial positions are around the equator of the ring, if you will. Okay, so let's draw a complete chair conformation. Okay, so starting in the beginning, we're going to draw the axial substituents. Okay, so first we draw our parallel lines, our three sets of parallel lines to give us the chair conformation. And then starting, if you call this carbon 1, okay, starting at carbon 1, we're going to draw a straight up axial hydrogen, okay, or axial substituent. So we go up, down, up, down, up, down. So axial substituents alternate on every other carbon between down and up. I got an extra one in there, didn't I? Okay, so then we draw the equatorial ones in. So here the axial ones on this next molecule are shown in red. Notice they're up, down, up, down, up, down. And the equatorial are shown in blue. So they're going to alternate down, up, down, up, down, up. Okay? So let's go ahead and practice drawing say, this molecule right here. Let's say we had methyl cyclohexane. And let's put that methyl group at carbon 1. So we could put it anywhere, right? But we're going to put it at carbon 1. So I draw my two sets of parallel lines this way. Now these parallel lines. Now these parallel lines, okay? Okay. So now I'm going to draw my substituents in at carbon 1. I'm going to have an axial substituent going up at carbon 2, axial down, carbon 3, axial up, carbon 4, axial down, carbon 5, axial up, carbon 6, axial down. Okay? Now my equatorial substituents. If I have an axial up at carbon 1, then I'm going to have equatorial down. I need to get a different color. That one's not working out. Okay? Then I have equatorial down. If I have axial down, then I have equatorial up. Axial up, equatorial down, axial down, equatorial up, axial up, equatorial down, axial down, equatorial up. Okay, so that's the way we draw it. And then if we had a methyl group on carbon 1, then I'm going to put that methyl group going axial up. Okay, then all the rest are going to be hydrogens. Okay. So if we have one substituent, there are two possible chair conformations, because that substituent can be in the chair conformation. Remember when we saw all the conformations, we had a left conformation and a right conformation where that C1 was up or the C1 was down. Okay, so if the substituent is on carbon 1, it can be axial up, in this case, or equatorial up. Okay, if we start out with axial up, then when the ring flips, that substituent will be equatorial up. Okay, so ring flipping occurs by rotation of all the carbon-carbon bonds in the ring, where the axial substituents are all going to become equatorial, and the equatorial substituents all become axial. Okay. So here we have the ring where we start out with the parallel lines with a positive slope. Okay, and so that's going to put, let's draw our axial substituents up, down, up, down, up, down. Okay, so now let's get equatorial. If the axial is up, equatorial is down. Axial down, equatorial up, equatorial down, axial down, equatorial up, equatorial down, axial down, equatorial up, and then we fill in all of those with hydrogens. Okay, now when the ring flips, this carbon 1 is going to flip down. Now to draw this molecule, we're going to start with the two parallel lines having a negative slope, and fill in the other two pairs of parallel lines. Now our C1 is down here, and our substituent that was axial up now has become equatorial up. Okay, so all of the axial substituents become equatorial. If it was axial up, now it's equatorial up. Okay, if it was axial down, now it's equatorial down. Okay, so now our hydrogen, let's call this HA, HB, and I don't want to do it that way. Let's just call this one HA. Let's just label that one. So now HA is axial down. Okay, so axial down, axial up, axial down, axial up, axial down, axial up, and the equatorial ones are now up, down, up, down, up, down. So all of the substituents that were axial are now equatorial. All of the substituents that were equatorial are now axial. But if they were up, they stay up. If they were down, they stay down. So here's what's happened. Our ring has flipped. Okay, our equatorial substituents have become axial. The axials have become equatorial. If they were up, they stay up. If they were down, they stay down. So we're going to look at a lot of different examples of this. So again, let's consider methyl cyclohexane, where the chair conformation, and we have the first chair conformation where the group is axial, and then we have the second chair conformation where the methyl group is equatorial. So most of the cyclohexane with methyl group on it is going to be in the equatorial position because it's more stable and there's less interference here. So we'll try drawing some of these. Okay, but if we have more than one substituent on there, we're going to have more interactions, and so we're going to have to consider that when considering the most stable conformation of that molecule. Okay, so even with just hydrogens, we can have some diaxial interactions. These are called 1,3 diaxial interactions because at the first carbon in the front here, we have a methyl group, and then the second carbon is the one on the circle of the Newman projection. Then the third carbon has got these two hydrogens, so they're going to interfere with that methyl group in 1,3 diaxial interactions. Okay, and so if we consider that having even more substituents, as they get larger, those interactions are going to interfere even more. So the 1,3 diaxial interactions are like gauche interactions, okay, and they're not present when that methyl group is equatorial. So if the methyl group is equatorial, then it doesn't have those 1,3 diaxial interactions, and so that's going to make that the more favored conformation. So let's practice drawing both chair conformations for each of the following molecules. Okay, let's start by drawing our chair, our cyclohexane chair. So we're going to start with our positive parallel lines and then fill in with the other two sets of parallel lines. Okay, let's number our carbons. 1, 2, 3, 4, 5, 6. Okay, so it's easier to start out with our axial substituent at carbon 1 going up, 2 down, 3 up, 4 down, 5 up, 6 down. Okay, and you'll see that when you make a model of this, that this is the way they're going to fall if your carbon 1 is the one if the carbon you're calling carbon 1 has an axial up substituent. And then we're going to do our equatorial substituents in. If it's axial, if the hydrogen is axial up, then on the same carbon we're going to have another substituent, or not hydrogen. If your substituent on carbon 1 is axial up, then the other substituent on that same carbon is going to be equatorial down. Carbon 2, we've got axial down, so we're going to have equatorial up. 3 has axial up, so we're going to have equatorial down. 4 has axial down, so we're going to have equatorial up. 5 has axial up, so it's equatorial down. Yeah, let's draw it a little better there. Equatorial down. And carbon 6 has axial down, so we have equatorial up. Okay, so we can just fill in the hydrogens on all of those carbons. But one of those wasn't a hydrogen, right? It was an OH. So let's take it off and put an OH there at carbon 1. So this is carbon 1. Now, it's going to undergo a ring flip, so we need to draw both chair conformations. Now, our carbon 1 is going to go from up to down, remember? So our first two parallel lines now have a negative slope. Then we're going to fill in with the rest. Erase that. Good. Okay, so now our C1 is here. 2, 3, 4, 5, and 6. Okay, so C1 moved down to here. Okay, so now everything that was axial is now equatorial. Everything that was equatorial is now axial. So if our hydrogen or our substituent was axial down, as in the case of this hydrogen, I'm sorry, if it was equatorial down, as in the case of this hydrogen, now it's going to be axial down. If it was equatorial up, then it's axial up. If it's equatorial down, it's axial down now. If it was equatorial up, now it's axial up. So at carbon number 4, we had equatorial up. Now we have axial up. At carbon 5, we had equatorial down. Now we have axial, And now I messed my thing up there. Now we have axial down. Okay. And at carbon number 6, the axial up, the equatorial up is now axial up. Okay, so all of our axials have now become equatorial. So that OH group is now equatorial on carbon 1, equatorial up because it was axial up. If it was axial down, now it's equatorial down, up, down, okay? And that's the 2 chair conformations for this compound. So which one's lower energy? The one where the OH group is equatorial. Let's draw the next molecule, both chair conformations. We start by drawing the 2 parallel lines with a positive slope. Then fill in the other 2 sets of parallel lines. Okay? Now our NH2 group is going to be at carbon 1, and we'll start with axial up. So that's an amine group. Okay? And we number our carbons 1, 2, 3, 4, 5, 6 around the ring. If the NH2 group at carbon 1 is axial up, at 2 it's going to be axial down. There's going to be an axial down, axial up, axial down, axial up, axial down. Okay? Let's get the equatorials. At carbon 1 I had axial up, so now I'm going to have equatorial down. If I had axial down, I have equatorial up. Axial up, equatorial down, equatorial up, and so on. Okay? So now we just need to fill in the hydrogens. Okay, so now we're going to do a ring flip. We're going to move this carbon 1 down. So now let's draw our 2 parallel lines. Okay, so we're going to ring flip this thing. Yeah, and it's not a resonance structure, it's actually flipping back and forth, so really I should draw this with 2 arrows. Okay, so now we have the 2 parallel lines with a negative slope. We start out with the ones with a positive slope, now these are negative slope, our first lines. So let's draw the other 2 sets of parallel lines to fill in. Now number our carbons, 1, 2, 3, 4, 5, 6. Our amine group was axial up, now it's going to be equatorial up. So we're going to have up, down, up, down, up, down for the equatorials. Now the axials are going to be down, up, down, up, down, up. So everything that was axial up is now equatorial up. Everything that was equatorial up is now axial up. Everything that was axial down is now equatorial down. Everything that was equatorial down is now axial down. Okay? So let's draw the last. So which one is lower energy? The one where our amine group is equatorial. Now our last molecule is exactly the same. It's just got a chlorine on it. So our 2 positive slope parallel lines, and then fill in with the rest. Number the molecule 1, 2, 3, 4, 5, 6. Okay, we're going to start out with that chlorine axial up, and then up, down, up, down, up, down. Now we're going to do equatorial down, up, down, up, down, up, and these just take practice, right? Fill everything else in with hydrogens. Now we're going to undergo a ring flip. That carbon 1 is going to be no longer up, it's now going to be down. after we undergo the ring flip. So now we have two negative sets slope parallel lines. Okay, carbon 1, 2, 3, 4, 5, 6. Now that chlorine that was equatorial up is axial up is now equatorial up. Now equatorial down, equatorial up, equatorial down, equatorial up, equatorial down. And everything that was axial is going to become equatorial. So this hydrogen well, I think I said that everything that was equatorial now becomes axial. This hydrogen was equatorial. Now it's axial down, up, down, up, down, up, and fill in everything else with hydrogens. Okay. Perfect. So larger groups are going to cause more steric crowding in the axial position. If a hydrogen is given a interaction of 1 kilojoule per mole, chlorine is going to be 2, OH is 4.2, methyl is 7.6, ethyl is 8, and so forth. Okay, and then this T-butyl is this is isopropyl, and this T-butyl is 22.8. Okay. And then the equatorial axial ratio at equilibrium is going to be 70-30 for chlorine because it's smaller. Okay, and then the OH is 8317, CH3 is 95.5, ethyl is 96.4, and when we get to T-butyl, it's 10,000 to 1. So the T-butyl group really wants to be in the equatorial position. So if we had a disubstituted cyclohexane, okay, then, and these here are on adjacent carbons and they're in opposite positions, okay, then when one is axial, the other is also going to be axial. When one is equatorial, the other is also going to be equatorial, okay? So if we rotate this molecule around, you can see that the chlorine is axial up and the methyl is axial down. So when the ring flips, now the chlorine is equatorial up and the methyl is equatorial down. So this is going to be the lowest energy conformation, okay? But if we have a larger difference, if we go back up here to our kilojoules per mole difference, here we have ethyl versus methyl. Ethyl is going to be 8 and methyl is 7.6. So that's 8 to 7.6 kilojoules per mole. The ethyl takes up more space and is going to be preferentially equatorial if we have to have a competition there. Okay? So let's draw both chair conformations for this molecule. Draw the first chair by labeling the substituted carbons in the given structure, then translating to a chair. So if I put the ethyl group at 1, and I'm going to rotate it so that that ethyl group is axial up on the first one, then the methyl group is going to be at carbon 3, okay, and that's going to put it equatorial down, okay. Now this can undergo a ring flip, and when it does, now the ethyl group is equatorial up and the methyl group is axial down. This is going to be the lower energy conformation because remember the ethyl group was 8 kilojoules per mole of energy and the methyl group is 7.6. So the ethyl group, if it has that 1,3 diaxial interaction, is going to be higher energy than having the methyl group in the axial position. So having the ethyl group, since it's larger, at an equatorial position is going to be more favorable. So of these two conformations, having the ethyl group, since there's a competition here, having the ethyl group in the equatorial position is better than the methyl group in the equatorial position. So we can't have both of those groups in the equatorial position at the same time. Since they're on opposite sides of the ring and one of them is axial while the other one is equatorial, the other one is equatorial while the other one is axial, we can't have them both equatorial at the same time. So the larger group being equatorial is going to be better than the smaller group, than the smaller group being equatorial, because the smaller group being axial is going to be better. So these 1,3 diaxial interactions are going to be lower for the smaller group. So let's draw both chair conformations of these compounds and see which is lower energy. Okay, so let's start by drawing our chairs. Okay, I think I'll just draw one set of chairs. So remember, we start by drawing the parallel lines with a positive slope. Then we fill in the other sets of parallel lines, the other two sets. Okay, now we start drawing the axial substituents up, down, starting at carbon 1. 1, 2, 3, 4, 5, 6. Let's number our carbons. So we start axial up, then the next one's axial down, then the next one's axial up, down, okay? Now we're going to draw our equatorial substituents down, up, down, okay? Now when this molecule undergoes a ring flip, carbon 1 is going to come down. Now we're going to start with our two parallel lines having a negative slope. Okay, now let's fill in with the other two sets of parallel lines. So now our carbon 1 has moved here. 1, 2, 3, 4, 5, 6. Okay, so now all of our axial substituents have become equatorial. So this axial up one at carbon 1 is now equatorial up. And now at carbon 2 it was axial down, so it's now equatorial down. At carbon 3 it was axial up, so it's now equatorial up. At carbon 4 it was axial down, so it's now equatorial down, and then up, and then down. Okay, so at carbon 1 we had equatorial down, and that's now axial down. So axial down, up, down, up, down, up. Okay. Now, if we number this ring on A, 1, 2, 3, 4, 5, 6, and we put our methyl group at carbon 1, which is axial up, then on carbon 2, we have an ethyl group on the opposite side of the ring. So that's going to be axial down. Okay, everything else is going to be hydrogens. So let's go ahead and fill those in. Okay. So now on carbon, when we flip on carbon 1, our methyl group was axial up. It's now equatorial up. And on carbon 2, our ethyl group was axial down. Now it's equatorial down. So which of these two conformations do you think would be lower? Well, on the left conformation, both of the groups are axial, and on the right they're both equatorial. So this is definitely the lower energy conformation for this molecule. Okay, so let's go ahead and examine molecule B. 1, 2, 3, 4, 5, 6, and you'll just have to practice drawing these chair conformations. I'm going to just go ahead and erase the substituents. And we've got them on carbons 1 and 2, so let's just go ahead and erase everything on carbons 1 and 2 to draw B. So I won't have to redraw the whole ring. Okay, so for B, if our methyl group is axial up, then our ethyl group is on the same side of the ring, so that's going to mean it's equatorial up. Since it's on the same side, we have to get both up ones. So the other hydrogens are down. Alright, so when we do a ring flip, our methyl group that was axial up is now equatorial up. And our ethyl group that was equatorial up is now axial up. So it's going to be over here. Okay? So having an ethyl group axial versus equatorial is worse. So this is going to be the lower energy conformation. We want our larger group, which is the ethyl group, to be equatorial. Okay, so let's go to molecule C. And just going to erase all of these. And notice that our first group is on, we could call, let me renumber that. Go ahead and erase this. Okay, so our first group, let's call this carbon 1 and this carbon 2 and this carbon 3, okay? Our methyl group is on carbon 1, and we'll call that axial up because it's on the pointing toward us on that side of the ring. So if we rotate this ring around and flip it sideways, then at the second carbon we just have hydrogen. So let's just draw those in. And at the third carbon we have a bromine in the up position. So that's going to be right here on carbon 3 where this hydrogen was. We're going to have, instead of a hydrogen, we're going to have a bromine. Okay, so that's axial. So here on our other molecule, the methyl group that was axial up is now equatorial up. And at carbon 3, the bromine that was axial is now equatorial. Okay? So on the molecule on the right, everything is equatorial. So this is going to be our lower energy conformation. So let's go ahead and do C. I did C. D, I mean. Let's just erase that bromine there. And I gotta put my lines back in. Just gonna do this last one. Okay. Alright, so let's call this 1, 2, 3. So that's exactly the same, except instead of the bromine, we have a methyl. So at carbon 1, we've got, oh no, they're just swapped. We've got bromine, and at carbon 3, up, we've got methyl. Those are exactly the same. I mean, they're not the same molecule, but they wouldn't be any different. Okay, the energy level. Okay, so now when we do a ring flip, the bromine is now equatorial, and the methyl group is equatorial. So on the right, we're going to have the lower energy conformation. Okay? So in the next topic, we're going to talk about cis-trans stereoisomerism, which we've kind of alluded to so far. And I'll see you next time.